PHYS Johnson, and this is my Lab 1 report for constant velocity. So to give a brief introduction of kind of the purpose of the lab and what I did, our lab requires us to observe and record the motion of some object, which in my case is a tennis ball that I rolled across the top of my dresser. And the point, we wanted to have an object that was moving at the same speed, so it had a constant velocity without changing its direction. And we used Tracker to analyze the ball's movement and change the position, where I adjusted the center of the object, calibrated the diameter, and set the axis, so we were able to accurately track that information. So our next goal was to construct a model on Glowscript using Newton's second law, which is F equals ma. And then we will use that model and compare it to our observed model that we tracked on Tracker. So just some principles is that according to the first law of Newton's is that my tennis ball should have continued moving at a constant velocity until some force acted upon it or stopped it. Newton's second law will be used in calculating the purpose or calculating the model for the predicted change in position of my object. So the purpose of the lab is to understand the application of Newton's second law so we can get a better understanding. We learned that the computational model is not 100% accurate to the observed model because of unforeseen circumstances that I'll kind of talk about later as we get into our results. Some important formulas and principles is the position update formula, the velocity update formula, which I used in my code, Newton's first law, which is that every object will remain at rest or in uniform motion unless it's compelled to change, and second law, um, for constant mass, force equals ma, or force equals mass times acceleration. So here's my tracker video um, that I put into tracker. The ball accelerates down the ramp. The velocity is constant, begins to become constant after initial increase after it goes down the ramp, and the ball eventually comes to an end after gravity forces it downwards. So to kind of explain the tracker process, to set up the tracker, we were to set the calibration of the diameter for the tennis ball, and then identify its coordinate system that would be used during tracking. I decided to start the axis where the ball stopped accelerating, and it maintained a constant velocity. And I also made the direction of the ball to travel in the positive x direction because the ball was moving right. And then after that, I identified the center of the object, and I used that to track its change in position with the diamonds. And I chose the beginning and end points at the bottom when the ball began its constant speed after it was done accelerating, and right before it fell off the table or the dresser. So we marked the change in position with the red diamonds, and as a result, we were able to get the table of data in the bottom right, and that produced the position versus time graph in the top right, which is positively linear but not perfect. And that's kind of due to those circumstances that I'm going to talk about in the results. But if we were to flip the axis, the position versus time graph would be mirrored about the x-axis, which means the slope would have the same magnitude, but they would be opposite signs. So this is my computational model. This is the coding I did. I manipulated the initial conditions, the time step, also set the F net to 0 since there's no forces that should be acting upon the ball since it's constant speed, and use the position and velocity update formulas. And I altered also line 49 to be 0.38 because that's how long my actual model took. And because of Newton's second law, acceleration must be 0 since the force is 0. And yeah, moving forward, this is our results of the computational model versus the physics tracker. The computed model is the red line and the blue is the observed model. The computed model is a great example of an ideal system where there's no external forces acting on the tennis ball. And the computed model is perfectly linear, indicating a constant velocity, but our blue observed model has a lot of disruptions and has much more variance in its slope. And some reasons for that variation are unaccounted forces such as air resistance, friction of the dresser on the ball, and the shape of the ball since it's not perfectly round. And if I were to replicate the lab, I would do it in a vacuum with like a perfect spherical ball, and it'll help mitigate some of those outside forces. So in conclusion, we saw that despite the computation model being close to the reality of the moment, there are factors and forces the model did not account for. When an object's in constant movement, the net force will always be 0, which is in agreement with the first law. And we were able to predict the movement of the ball using the update position and update velocity formula, both derived from Newton's first and second laws. So what does this all mean? In the simplest scenario, there's at least two forces, gravity and normal force. If there are some horizontal forces like friction and applied force, there would be at least 4 forces in total, and it's not possible to have an accurate account of all the forces acting on the tennis ball, but we are able to list majority of them. Regardless of the number of individual forces, their vector sum must be 0 for the object to maintain a constant velocity. Thank you.